Hello, good morning once again and welcome to my YouTube channel. So this is now the last part of the session for animal science dataset. So first part is all about data visualization, and second part is descriptive statistics in animal science, and the third part is basic plots in R, box plot, histogram, scatter plot, and also some simple correlation plot among numerical data set. And the fourth part is linear and multiple regression. So today, let's have end the session with the parametric and non-parametric test. So this is where actually you ran ANOVA or unless a variance for the t-test or the, what do you call it? Um, Non-parametric, the Presley-Wallace and Mann-Whitney test. So for that, let's jump in. So this is my YouTube channel. Just whatever you need, just browse the videos that you wanted to learn, and you can you can apply it in your own data set. So let's jump in. So let me just clear this so that you will have an overview what we're doing right now here. So again, this is your our studio. I already wrote here the code that I wanted to have a clear um code so that you will understand exactly what we are doing. So in this case, we were just trying to understand how to run ANOVA, t-test, and course Kalwala and man-Whitney test using as a non-parametric test. So this is just how to load the library. If you don't have here, just go to packages and install, and just type in the tidyverse, and there you go. Just click that, and but I'm not gonna do that here because it's already installed. And let's just create a dataset because right now I don't have a dataset. So let's just create a dataset. So this is how we create a dataset. So treatment, control, feed A, feed B. So I have to make sure that we have three groups so that we can use ANOVA. ANOVA only works when there is more than two variables. And for we have the weight gain, the feed intake. So this is just like the minimum on maximum control, but next time we will use an actual data set. So, but for now, let's just stick to this idea. So for a data set, we have 60 observations. Out of three variables, you only have treatment, weight gain, feed intake. And if you try to look at the data, you have fracture, number, and stuff like that. So again, if we wanted to make it data, so let's just set this names data. So treatment again, and that's it. So I'll just have to write data and uh weight treatment. Let's take the treatment is equals to as factor. Then data treatment. So you can just double check it here. Treatment, it's character control. If I'm gonna run that, it will have factor with three levels. Now we can somehow use ANOVA for this. So now we have it. Let's just have a quick visualization. So this is very easy. So just, don't want to delete that and focus on this here on this code. And here you can say the head. This basically we have this in our previous tutorial. So, and the structure and also the summary and the summary of what we have here. So weight gain minimum, feed intake, control, you will have the 20 observations for the control and 20 observations for feed A and 20 observations for feed B. So to check if our data contains not missing values, we just have to run this call sums in that data. And so far our data is complete. So you don't really have to run this. But this is how you remove the observations of or a column variable that has no value. So let me just delete that because we don't need that for now. So let's stick to a simple descriptive statistics. It's very important, to those descriptive statistics. So this is from the dplyr library, dplyr. Just run that. So again, this is how you write the code data. This is the pipeline, and we wanted to group by treatment. And again, always put this one. And this is where the code begins, summarized by the mean gain weight and the standard deviation of gain weight, and this is the number of observations. So just run that, and there you go. You can see. But I wanted to, what is summary treatment? And I will just go like this, put an arrow, and if you can see here, we will have the so-called summary treatment. Three observations, mean gain. So you have the same observations, but you can see the mean gain is, fit A is much more higher. Fit A is 1.9. So like contour is lower. So you can see fit A is much more, just looking at the mean gain. So fit B is much better among other three groups. So to write that here, see that CSB summary treatment and the name of the table that you wanted to treatment. I'll just put this another, that's CSB. So if you try to go back to your R, you can see your date modified. So this is summary treatment ANOVA. And you can just copy this already in your Word, and then you can create a table, or you can ready to create a table for reporting. So it's a bit easy actually. And if you don't want to do that, you can just delete that, delete, 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 delete. So this is how you report your table for publication. I mean, also for your thesis. So it really depends on how you kind of want to report, but it's important that you know what you're doing so that you will understand, of course, what's your, and that's it. So see, you can see that fit B is, it's much more better, but let's go back to our R. So with that, we can here. So before we will kind of, because based on what we have, fit B is better, but then we didn't really know if it's really highly significant or not. So we are just looking at the mean. So maybe there's something that we can already tell, but if we'll try to, so average, standard deviation, and this is how you check the normality. Let me just copy that to here to make it more clear. So what we're doing, I want to close that. So Shapiro, that test is how you checked the normality. So Shapiro the weight gain. So your p-value is 0.2. So if your p-value is higher than 0.2, it means our data is normal. So we can also verify that by looking at this data. Let me just copy this one here directly. It's more easy. So you can see this looks normal to me, and also from the p-value, which is 0.32. When p-value is higher than 0.1, it's considered normal. So we can also check that by running this. So the histogram, main histogram, actually you can just, run like this. It's just the same, but some like that. And but if you want, like some statics, so you can just do like that. Another X log. Oh, okay, happened. Weight gain. Okay, yeah, histogram is the same. But if you don't want to, just delete that. Actually, you don't need it. And if you don't want to, and we run it. So no, but of course it's important for you to have some kind of a legend. So QQ norm, the normality, the line, and the QQ line here, just to check if it is indeed like our data is normal. So you can just rotate it per line. So looks perfect to me. The data falls directly to the line. So we can say it's kind of it's it's normal. So now let's try to look at homogeneity of our data. This is very important when you run an ANOVA, right? So this is how you do it. It's the same with linear modeling. So you put the response variable and your predictor, which is also the independent variable and dependent variable. So that's the linearity test. Just run it. And the p-value here is 0.2, which is greater than 0.5. So we have equal variance. So which is still, it means that we can now proceed to our parametric test. So either we can use ANOVA. So ANOVA, this is just how it's done for ANOVA because our assumptions are already clear. So we can now use ANOVA. So based on our tables here that PB is much better because it's much higher, but we don't really know which um, treatment is significant or not. So let's just check here. So again, it's the same with linear modeling. So just type here the response variable and also the predictor. So this is, you can just do like that and you will already have so-called here. But it's better to have because we want to extract the value. Just make another username and there you go. And you can type summary and album and there is the upper result. So treatment, so see, we can now see that treatment there is a highly significant. That's 3 stars. It means that p-value should be like 0.000 something like that. So, but based on the idea that based on the p-value, actually you can just copy this as well, so that you will have an idea that your ANOVA, your treatment is highly significant. So you can copy like that, and then I'll just make that this somehow summary and here insert comments. This one, then you understand. Now, but because we don't know which, we learned the fact that it's highly significant around trigger, but we don't know which is significant. So maybe both B and E or E and D. So that's why this are so called the post hoc test. You can only apply this when it's highly significant. So ANOVA or an ANOVA model here, and let's run a Tukey. And based on that, we can only see that 0.5. So it means that all values are highly significant. So control A will be, so only it's highly significant. B and A is control. So, but A and control, as you can see here, A and control, which is so close, 1.5, 1.9, but then it says here that it's 0.00, but still it's highly significant. That is making sense to us. So now, at least 100 papers and the non-parametric test. So imagine that our data is not homogeneous and is not normally distributed data. So that's why this is where you apply this, a non-parametric. So it's the same with just, but you have to use the first Wallace test. This is like stands for ANOVA. Add the same coding, just run it. And here is the p-value, which is negative is point something something, so which still is also significant. And for the post hoc, instead of two key, you for the non-parametric is so-called Dantes, the Bonferini. And then you can just run it. So treatment data method and run it again, and then you can see p adjusted is 0.001 or 0.00. So still it's highly significant. And that's how you run a non-parametric test using the post hoc and use if not normal. So this is optional, but let's just you run it. So this is weight by gain, but this is like not so good. This is only a basic, but you can already report like this. Here you are, but in my case, I will just remove the main to make it more professional. And then I'm gonna save that like that and just box plot treatment, something like that. And then just have to go back to where your data, I mean, like did modified and box plot treatment. So then you can just copy it and put it in your thesis or whatever that is, your publication. And there you go. And you can just say figure one, something like that. Write caption. So that's exactly pretty easy. And for that is, let's say, for the digiblock, it's more professional. I said for the digiblock, just type in there. Already have a tutorial for that. So data, treatment, weight gain, backspot minimal, and then just run it. And there you go. I think it's more professional and clean and clear. So I prefer this, say, backspot treatment. And again, just go back to see which one is much more professional. Which one do you like? So I would say I would prefer this one. So I'm gonna delete that. And then figure two. And I will say box plot of treatment of feed intake in cattle farming. Something like this. So now you can see, oh, control A, control B, and stuff like that. It's more yeah, it really depends on how you write your story about it. It's already part of you, and that's why it's important if you're the one who analyzes the data, it's important that you know what kind of story you want to tell to your reader. So you can see that feed B is much more better in terms of the gain than control. And if you are like somehow uh out of budget, so it depends on you. So you can see, just look at our table here, treatment, main gain. So feed B is much better in terms of main gain, and feed A is 1.9, which is almost 2. So like a scientist, as a researcher, you have to decide what is the best for you, and that's the time that you can have to recommend what is the best. So you can just write like this. So I'm just this is just an example, you can write your own, and let's say like this. So you can say there was a single effect of treatment weight of gain. You just have to write the p-value on the estimate, and then you can have table or figure one, or you can just write this your table. This is table two. So table two. So just put it there, table two, okay, and then you're good to go. So two key based on difference and control base, blah blah blah, and non-parametric control difference, and then you can say figure true. So I think that's the end of the story here. Exactly, this is what I'm all about. And thank you for watching. And again, um, write me email, and if you need help with data analysis and data visualizations, if you think you need someone to do like speaking engagement, I am very willing to give a lecture on data analysis and or other stuff. So my YouTube channel is all about data analysis, scholarship, and also academic success, travel inspiration. I have traveled 28 countries and also applied a different scholarship. I had a scholarship from Germany for my master's. I have a scholarship in the Philippines under the UST for my first master's, and also my third scholarship in Europe. My PhD scholarship in Czech University of Life Sciences in Prague. So please try to contact me if you need some help, and I think that's all. So I hope you enjoy a lot today, and I'm happy to help you out. So let me just end this.